Hey Keith, we got lecture 15. I thought we'd talk about confounds and problems.
Sounds good. Let's get into it.
Yeah, so this is going to be a nice follow-on from some of the prior lectures that we've talked about. The first thing, so that you can see here, there's a bunch of things to talk about. And I think this lecture might be a little bit shorter than some of the others, but probably okay, because I think that maybe some of the others are a little bit long.
Yeah, they have been. So Kim, today what are we getting into here? Just things that people need to think about when they're reading papers and designing experiments, right?
Yeah, yeah.
Like generally.
Yeah, so we tried to come up with just like a whole bunch of problems and issues, and it's just a little bit of a list, but let's just go through it and see where it goes.
Mm-hmm.
All right, so let's start out first of all with the fact that one of the problems here is that there are many things going on at the same time. So, we've talked about this a couple of times, like all these different things that are happening. So, first of all, we don't really know exactly what is the physical effect that we're particularly interested in, but there's so many things happening because we have pressure waves, and the pressure gives rise to an intensity. There could be standing waves when you're talking about intracranial applications. And, that was a picture right there showing you the standing waves that are being modeled inside the mouse head. We talked a little bit about radiation force. If there's a nice focus, you can have a force that could give rise to stresses and strains. Some of the tissue is going to be pinched while other tissue is going to be pulled. There's shear waves happening at the same time. So whenever you have a focus that gets pushed, then the shear waves are going to develop from that. There's potentially a rise in temperature. We think that we are operating where we're at very low temperature rises, but there's always the potential for a rapid rise of a quarter of a degree, or a rapid rise of a tenth of a degree, and would that have an effect? There could be potentially cavitation that could be kind of within the membrane and unmeasurable. There's particle displacement. So it's just really, the point here is there's a lot of things going on all at the same time.
Yeah, and when you're reading papers, you can sort of listen to what they're saying about any individual metric, but because they're going to affect others, maybe a lot of others, you need to draw your conclusions from multiple sources.
Yeah, and the nice thing is I think we've gone through what each of these mean so that we're all better informed about the possibilities for multiple things happening at the same time.
Mm-hmm.
Well, I guess that's really about all we really wanted to say there. Is just kind of bring attention to the fact that it's hard to separate these. One of the things we tried to do is look at the frequency response. And there's some information that did provide, sort of whether or not cavitation and particle displacement were different than temperature and radiation force on different opposite ends of the spectrum. Although it's not totally clear that we have a good finish the story on that. But anyway, yeah. All right, let's move on then to our next one, which is something that we've just been talking about a little bit about the problem with anesthesia. So I may have mentioned it already in one of my slides already. And the idea here is that, of course, that if you're going to do an in vivo experiment, then in order to keep the animal still, then they have to have some anesthesia on board. So right here, this is the mouse, his nose is up into a nose cone, and he's been given isoflurane. So this is a gas, and that will help him to keep still. We did do some experiments where we were looking at the effect of anesthesia, and I'll come back to that prior slide just a moment. And what we found, these were the ultrasound pulses, and then we were looking to see the EMG response. And we did this at 3 different levels of isoflurane. So 0.5% isoflurane, which is itself low, because usually they expect you to keep your animals about 2% isoflurane. And so that was a bit low to begin with, but you can see there aren't any responses, EMG responses. And then when we lowered it to 0.1% isoflurane, you can see that there's nice responses right there to the ultrasound. A little bit lower in the isoflurane. Again, there's really nice responses. There, with the mice and the experiments that we did, there was some number of twitches that were sort of spontaneous twitches, and so they gave sort of a baseline level of response. And so we always were comparing, was the effect of the ultrasound above that baseline level? But nonetheless, it definitely is something to be aware of, is that the effect of anesthesia affects the response that you're going to get. And not only that, I didn't write it on this slide, but also whether or not the isoflurane is carried on just air versus oxygen also has an effect as well. And then the flow rate.
So when you're doing animal studies, there's always sort of this ideal of, can we measure all these things in a freely awake and behaving animal? And the answer for many studies is often no. So you look at the study, they have to use some sort of anesthetic to keep the animal, for the measurements. And Kim's pointing out here, what's important is, if you don't see a response shown in the top graph here, is it because you've just anesthetized the animal so deeply that these nerves no longer respond, or is there truly, no response to ultrasound? So that's the balance here.
Yeah, let me just go back a moment to the prior slide where we were talking just here. It's just some points. There is a trend to try to do these experiments rather than giving anesthesia, to have a small device that could be worn on the head as they're moving around freely. Or another possibility is that the device could be fixed and the head fixed to the device, but then the platform that they're on could be movable so that they could feel as if they're moving around freely, even though their head is kept still. So there's different options there, and definitely people are thinking more about how to do this without anesthesia.
We can also mention really quick before we move off of anesthesia, I don't know if they would have seen Scott Hansen's lecture before or after this, but there is certainly an anesthetic direct interaction with how mechanosensitive cells are. And how that works exactly and how that interacts is not entirely clear, but it's something to consider, especially when you're trying to choose different anesthetics.
Yeah. The animal temperature is also a bit of a concern, that it could, when you use an anesthetic, the temperature of the animals tend to decrease. That will decrease their metabolism. If you use something like an injectable, then that changes the rate at which they metabolize the anesthesia. So it's also just, potential confound.
Oh yeah, especially if you're looking at cells in the brain that sense subtle temperature shifts, and there are many of them. So, if you're decreasing temperature and they're heat responsive, then they're going to shut off, even if you're stimulating with ultrasound.
Mm-hmm. So we've also done some experiments with ketamine and xylazine. Many people in the field have used that. Just anecdotally, it seems like we get better responses with ketamine xylazine after it wears off to the point that we get responses. So typically when we inject it, it just kind of, there's no response at all. And then you just wait for him to metabolize a little bit and do the toe pinch. And at some point he will respond, and then you can do experiments. And we've had actually better success rates with it, but it's a little unclear why. And then also the other problem is that it's it's the amount of anesthesia is varying over time as he's metabolizing it. So it's unlike isoflurane, where you kind of keep it constant. You can keep it constant. It is sort of a variable that you can't measure what the anesthesia level is with ketamine xylazine. You only have a certain window before it's worn off altogether. All right, anything else there?
No, I think that covers it. That's our next topic here.
All right, next topic, the auditory confound. So I actually have a little bit to talk about here. Just as a background, there's a number of papers that we wanted to talk about as sort of background leading into this. And the first one is the fact that when you apply an ultrasound to an animal's, to the head, it's actually been known for a pretty long time that they can hear something. So there's this paper that was back in 1978 talking about sort of the cochlear response that you can measure when you apply the ultrasound, that in the cochlea, you can measure a sinusoidal response. And so that's actually been known for a pretty long time. More recently, I guess we weren't really sort of paying attention to this issue. And then there was a pair of papers that were published about a year or two ago that pointed it out again. And it was really, I think, very important for them to point that out so that we would kind of paying attention to this issue. So one of them showed that if you apply ultrasound to, I think it was in a guinea pig, that if you cut the the nerve to the ears, then they no longer responded. And the other one was showing in mice when they had some G-camp imaging, that they showed that when you applied ultrasound to the brain of the mice, that the G-camp images showed that the auditory cortex really lit up, and not necessarily the area right under the focal spot. And that was sort of combined with this prior paper that was sort of completely different, but related in that it was saying that if you have sound-driven, a very large sound, then that could inhibit other activities in the brain. And so that was sort of explaining perhaps why, if there was a very large auditory stimulus, then maybe it was inhibiting other responses. And so one of the questions was, well, what exactly are the animals hearing, and is there something you can do about it? So anything else, Keith, about the sort of background leading into this? And then I was going to talk a little bit about the work that we did.
No, I don't think so. I think you covered it.
Okay, so those references are given there. And so we did some work looking at measuring the auditory brainstem response. And so this is just a matter of putting electrodes in the back of the animals, subcutaneous electrodes. We were able to apply sound to the animals as well as apply ultrasound to their head. So we did both. First of all, let me just walk you how this ABR works. It's just that when you apply sound, for example, then this is ABR responses to 16 kilohertz sound. And then when you increase the sound level, so here at 20 dB sound pressure level, and then increasing, that you get this response on the electrodes. And then when you have a discernible response, then you can say, well, that can be heard by the animal. And so this 20 dB seems to be sort of sub-threshold. And so this is just the response you would get from a wild type hearing mouse.
So Kim, you're taking like sharp metal electrodes or like wires and puncturing through the skin? Okay.
Yeah.
So the animal, like if you're even listening to that, of course, it's easier to do this if the animal is anesthetized, or else the electrode itself will get moved while they walk and it'll be hard to position and so on. But
I think the anesthesia doesn't affect this pathway. So this should still, despite the fact they're under anesthesia, I don't think that that affected these measurements.
Oh, sorry. I just meant like the motion, if the animal's awake and moving, that the electrode will get bounced around.
Yeah. Okay, so we had 3 different types of mice. We had our wild type hearing mice. So those are the ones on the first row here. And they're just showing you here is that as we applied a sound at 16 kilohertz, that they were able to hear it. So that just sort of here for comparison is what a wild type hearing mouse, what their ABR response looks like. And then for every frequency, you can see here plotted out versus frequency is what is the sound pressure level when you finally do actually get a response. And so that's sort of the threshold. And when you plot that out, you get a response that looks like this. And so this is saying at a low level, about 20 dB or 23 or 30 dB SPL, then you get a response at these frequencies. And if you go up to this frequency, you have to go much, much higher in order to get a response. And so this is telling you sort of, how good their hearing is. We also looked at these 2 different genetic knockouts, and these 2 different types of mice were deaf for different reasons. And you can see that as you increase the sound pressure level, we never got a response like we did in the wild type hearing mice. And if you plot out the thresholds, you can see that we went all the way up to 80 dB SPL, and they still, we stopped at that point. So you just draw the line there at 80 dB SPL saying, that we didn't get any hearing response below that. So two different genetic strains. And then what we found was that when we did the experiments where we applied the ultrasound to their head and we're looking at their EMG responses, and we plotted out success rate, and this is now as a function of the intensity of the ultrasound, that the genetic deaf mice and the hearing wild type mice responded at the same rate. So here for the one set of genetic knockouts, and then over here for the second set of genetic knockouts. And so that was saying just right off the front that it's not that hearing is the sound is necessary in order to have the response that we were measuring. Okay, so we went one step further in order to look at, well, what is it about the waveforms? So we looked at 4 different waveforms here, and most of our experiments had been a continuous wave with a rectangular envelope. And so that meant that it was just on for 80 milliseconds straight, and the envelope was rectangular, and that it went, sort of instantaneously on and then instantaneously off. And what we see is that there was a response right after the on, and you can see that this is the ABR here, and then also with the off, there's an ABR. We looked at also 2 different pulsed waveforms, and they're just at different frequencies. So this was an 8 kilohertz PRF, and then a 1.5 kilohertz PRF. And then you look at the ABR for both of them, and you can see that, again, it's right after the on and then right after the offs for both of them. And then this is really interesting. And here, it seems like there was maybe like a little bit of a response during the 1.5 kilohertz that they could hear something throughout. So that makes some sense. The hearing response does happen a couple of milliseconds after an initial change in the sound pressure level. And so if they were hearing something from this ultrasound, it wasn't that they were hearing it during the flat part where it would be kind of a constant tone, but hearing it right after the on and the off. So that all made sense. We also did an experiment where we intermixed here the continuous wave, but we smoothed out the waveform. So you can see how smooth it is on the on and the off. And what we found was that there wasn't an ABR signal from that waveform. So, and again, these experiments here now are done in the wild type hearing mice. So, I mean, that just shows that the waveform affects what they hear, and it gives us sort of a method forward for how to design these experiments so that the animals don't hear anything. We just have to design the experiments with a waveform that's smoothed enough so that it doesn't trigger an ABR response or a hearing response. Okay, so just one step further now. So this is now sort of what are they hearing? And so this is a sound click at 40 dB SPL and sort of the amount of the ABR signal. These are the 2 different pulsed waveforms, the CW waveform that we'd always used up to that point. And what you can see is that the amplitude of the ABR response was much smaller than that 40 dB sound click. That 40 dB, just to put it sort of in perspective, is about, I measured it with my iPhone. You can say, well, what's the ambient noise? And just sort of the sound of like the fish tanks in the dining room was about 40 dB SPL. It's not enough to make me startle or the, mice. So just to sort of put that in perspective. We kind of looked at the signal under these curves. This is the ABR signal power. And then what we found is that the signal power for the smooth is really quite small and not significantly different from sham, but significantly different from all of the others. And then lastly, using the different waveforms down here at the bottom, and this is red is the hearing wild type mice, and then gray is one of the genetic knockouts, is that the genetic knockouts respond at the same rate as the hearing wild type mice for all of the different waveforms. So, I mean, what that's saying is that, yes, mice can hear the waveform that's applied. What they're mostly hearing is not, of course, the fundamental. So the fundamental for these experiments was at 500 kilohertz, and that's way above the hearing range of mice, which is about 1.5 kilohertz to up to about 90 kilohertz. But what they're hearing is sort of the envelope. And so it's and mostly it's the high frequency components during the on and the off of the envelope.
So Kim, I feel like you might already have this too, but if you do a Fourier transform of your signal and you look at the broadband spectra, can you assess like a priori whether or not they'll hear it?
Yep. So that's such a great question, and we're doing that work right now. And so you would say, let me rephrase that, you could say, well, can we design some waveforms or design a method for understanding the waveforms so that we know that what they're going to hear is below their threshold. And so, it's entirely possible this, for example, was too far smoothed and we needn't have smoothed it quite so much. And so we're looking at that exactly. So what are the frequency components of the different waveforms in order to be above and below that threshold, so that, sort of prospectively we can design waveforms to be below the threshold. Okay, so given that, yes, they were hearing it, but it was not terribly loud. In our data, it looks as if it was below a 40 dB SPL, and that the animals respond at the same rate. That we thought that was pretty good data, that it wasn't because of the sound that they were responding with the EMG and the forelimbs. We went one step further to further evidence against it being a startle response. And that is that we changed the duration of the stimulus. So here, 80 milliseconds, 160, 320, 640. And what we see is that in the EMG that the response changed the duration as well. And so that's not something that you would see if it was a startle response. The startle response would be that it would come right after the onset of the ultrasound, and then it would be a similar startle for each of the durations. And so given again that wasn't what we saw, we also again thought that was like further evidence against it being a startle response. Okay, so that's about all I had to say about the auditory confound. Well, actually, there's a couple more things. One of them is that there's some nice work happening at Oxford. Chris Butler and his postdoc have done some work where they were looking at some human studies where they applied ultrasound, and the humans could actually sense the ultrasound or hear it. And then they applied noise canceling headphones so that they could kind of mask out the sound that was heard by the subjects. And so that's also some additional work kind of corroborating the auditory confound.
Could you comment a little bit on how you think the sound gets from, so obviously the ultrasound is coupled to the skull and not to the ear itself or the cochlea. So I think you've said in the past, it's like it may be shear waves propagating across the skull.
Well, that's one possibility. Mikhail Shapiro, who we'll hear about later in the class, he's done some work where they did some modeling, and that when the ultrasound hits the skull, then shear waves propagate across the skull and into the ears. Mm-hmm. It could be that. It could be that there's some oscillation of the tissue and the CSF, and then that inevitably sends some pulsations into the ear. So there's different possibilities.
Yeah, it kind of sounds like it could be a cool way to allow people to hear things without putting headphones in their ears or over their ears. I don't know when that would be useful, but.
Well, actually, it's long been known in the auditory field that you can have speakers that you apply to the temporal bone, and then you can.
The bone conducting speakers?
Yeah,
okay, cool.
Yeah, I just wanted to get back a moment to what I was mentioning with Chris Butler's work with humans and how they had the cancellation and just the importance of when you're doing a study of having sort of the sham, the control and or the sham, and that if the subject knows when the stimulus is on, it's not the same thing as not knowing, right? You always want to have a sham condition so you can say, well, when you're stimulating, it's different from the sham, and not have it be known. So a blinded sham study. So that's why this is so important to kind of get rid of the sensation or being able to tell. All right, shall we move on? Sure. Electrode displacement artifact. I think these slides are yours, Keith.
Yeah, and I can sort of intro into the idea here. Before we even talk about the slides, a lot of studies that you'll see, involves some sort of electrode directly measuring either electrical current or a voltage across the cell. And if you're thinking about this, it's inherently subject to the fact that the cell membrane is moving and the electrode may or may not be moving the same. So in one possibility, where the recording electrode is actually recording from is changing, but also the membrane may be affected because this large bulky device in it is not moving the same. So I don't know if that makes sense, Kim, the way I'm saying it. You may have a different way to say it.
Mm-hmm. No.
So no, everyone kind of talks about this and asks about it. It's very early in terms of being examined. Usually people will brush it off when you ask it. Oh, I don't think it's a big effect. But there was one paper recently that we're going to just show here from Morgan Collins and colleagues, where we'll play the devil's advocate and say, this paper isn't exactly perfect, but it definitely shines a lot of light on the possibilities. And what they did was took the leech animal model, and in the figure on the left here, you're seeing sort of an image of the Retsua cells within the leech labeled by that R. And these are just extremely large cells, and they're very easy to stick a sharp electrode recording into. And because they're so large, you don't typically damage the cell. You can record for a long time. And on the right-hand side, you can see a preparation that they put together that was very nice. On the top, this little holder, I don't know if you can see my mouse, but Kim, maybe you can highlight this. They have a micromanipulator arm holding that electrode pipette. Kim, if you could show them the pipette. And they're basically lowering it into the Retsua cell, which is in saline here. And below it, they have their ultrasound transducer, which can cast an ultrasonic field onto the cells while recording. And if you could go to the next slide. So on the left here, you can just see that if you look at the normalized pressure field over their prep, a large portion of the pressure falls directly onto the cells. But some of it, is falling onto much of the electrode in this image. And certainly the electrode is directly in the prep. So keep in mind that your ultrasonic field is going to move the cells to some degree, or the cell membrane with these waves, but it also may affect the pipette itself. And if you can hit next.
Yeah, can I just ask, so there are transducers below and it's coming up, and then is this all fluid here?
Right. So that's a coupling agent below the slide, and then there's a saline tank below that line.
So this is a fluid air interface?
Right.
Okay, so they're probably going to get a lot of standing waves in here because it's going to be reflection at that interface.
I think they definitely could.
Yeah, okay.
So again, we're being critical, and we're just showing you how this work may or may not be useful. So what they did was to ask the question, if the electrode moving from the ultrasound is responsible for at least some of the ultrasound measured changes in electrical activity, then moving the electrode should give us a similar readout. So on the top here, the pink line is showing you a short pulse of ultrasound on. That's where that line kind of ticks up. And you can see the electrical response of the cell. It's sort of a sharp upswing, and then the signal decays back down. Now below that, they're taking the micromanipulator, which holds the electrode, and simply moving it up and down within the prep. And they're not identical. You can see there's sort of a slower onset, but what you can see is that both of these manipulations will give you a deflection in this electrical activity. And if you hit next here, Kim, you can see a quantification of that. So they were able to measure across different amounts of pressure delivered, and you can see that the cell is depolarizing, and they were able to mimic that by displacing the electrode. So as the devil's advocate, this is certainly interesting because the curve can be mimicked. So it suggests that yes, it's possible that the ultrasound effect is coming from the electrode moving. But I would also say that all biological phenomena have sigmoidal curves, and you can continue moving this electrode, at any rate to find a curve that matches the one of the ultrasound. And this group, unfortunately, did not measure the actual displacement of the electrode. So we don't know if 80 kilopascals of pressure actually maps to the electrode moving 2.5 microns, but it does suggest that this sort of interaction is possible. Okay, so this is a little bit of a complicated experiment, but I'm going to do my best here. One way to more directly examine whether or not the electrode moving from the ultrasound is responsible for the cell's response is to remove the electrode during the stimulation, during the ultrasonic stimulation, because in this way, the electrode can't move within the cell because it's just not there. So this figure sort of illustrates that they will put an electrode into cell A, which is shown on the left here, and they'll record some baseline amount of activity. Then they'll remove that electrode and deliver an ultrasound pulse for a given period. And then they'll place the electrode back in, shown on the right, and record again to see how the activity of the cell has changed. Now they did one further part of this experiment, and to preface, when you're puncturing and removing the electrode from the cell, there's always the possibility that that disruption of the membrane may cause changes in excitability. However, there's this nice benefit of using the Retsua cells in that there are always two of them. So here they're labeled A and B. And even though they're distinct cells, they're electrically coupled in such a way that whatever one cell is doing, the other cell will generally be doing the same thing. So you can affect mechanically and with the puncture cell A without affecting cell B by puncturing it and still measure what the output might be. So that's sort of a useful tool. So Kim, I think if you hit next, the electrode's just going to flip over. But if you can hit next again, we'll go to the results. So on the left-hand side here, you can see the recording pre-ultrasound. You can see a given amount of spikes per second. It looks like about 1 spike per second. And then they remove the electrode and perform the ultrasound. And you can see that in the post-ultrasound trace on top, not only is the resting membrane potential higher and closer to spiking, but that there are just more spikes in response to that. So it was clear that the ultrasound had done something, except that the electrode was also removed from that cell. So was it the ultrasound or was it the removal of that electrode? So on the right-hand side, you can see the quantification of the experiment I just described, where there's measurement pre and post from that same cell, and you can see it increased spiking, as we said. And on the right-hand side, you can see that they measured from from the other Retsua cell that is electrically coupled, but in no way interfaced with the electrode, and that you still sort of get this change in excitability. So I do realize that they wrote not significant on the top here. And I don't want to say for sure, but I think they're doing that to say that their point is still correct and that this other cell that isn't touched by the electrode is unaffected. But clearly you can see that some sort of effect is happening and that the data was undersampled. So what we're trying to say here is that yes, their data shows there is some impact of moving the electrode within the sample, even though we don't know if ultrasound would move the electrode in the same way, but that with their same preparation, you can see some effect of ultrasound on the electrically coupled cell that seems to be totally independent of the electrode moving. So Kim, you can comment. I know I've just said a lot, but I guess I would say the jury's not out, even though I think this paper does a nice job of highlighting the potential confounds of stimulating the field that your electrical recording equipment is in.
Okay. I don't think we have a slide on this one, the patch clamp seal disruption.
No, I think we could just talk about it though.
Yeah.
So what is that, Kim?
No, you go ahead, tell us.
Okay, so if we've already learned about patch clamp, that is where you take a very smooth but very small electrode and you basically create a small suction onto the membrane of a cell. And by creating that seal between the electrode and the cell, you can measure individual currents as they pass through within that electrode. Now, the problem is, even though we'd like to measure the currents from selective types of channels within this prep, the very small electrode can't actually hold on to the cell at lower frequencies. They find that, when they use anything, I don't know the exact divvy here, but when they use anything sort of in the low megahertz or below range, that the hold on the cell is quickly disrupted and that things move around and they can't hold that seal between the electrode and the cell. So all of the papers, and you'll see some from Merit Maduk's lab specifically, and Pierre Curie-Yacoub, they always use 43 megahertz, and it's a very high frequency. So they get around this problem, and they really use it because they also just had a 43 megahertz transducer laying around. I'm going to leave it up to Kim to explain why this might happen.
Well, actually, I'm not sure we totally know why it happens. In fact, I emailed with Pierre and with Merritt, and they weren't quite sure either. But, I might hypothesize that one of the things is that we've talked about is a particle displacement. And the particle displacement goes as 1 over the frequency. So it's just, there's bigger particle displacement. And so it's entirely possible there's sort of at low frequency more time for the movement of molecules and disruption of the seal, whereas at high frequency, there's not that much sort of waving around of the molecules and not that much time for the disruption. So that's just my best guess as to why the very high frequency seemed to work here. There's always these questions about, well, how applicable is the very high frequency? And the truth is, if you just really can't get that data with the low frequency, then, high frequency, it provides some data. So, I think it's important work to keep that in mind.
Yeah, and if you're measuring a particular feature, like Steve, likes looking at radiation force, then it shouldn't really matter what frequency you're using, and you can just tighter the displacement accordingly.
All right, so next one is transducer heating. I think you do have a slide on that one.
Yeah, I included a slide on this from my own work. So we'll just kind of preface this with, sometimes your transducer is close enough to your prep. Let's say I'm a human and the transducer is directly against my skull somewhere, maybe in the front. And the voltage being cast across the ultrasonic elements or the piezos actually generates some amount of heat. So you always have to ask yourself, is the effect I'm observing because of the ultrasound coming off of this array, or is it because of the heat generated by the ultrasound itself, which may also pass into the skull? So a number of my experiments have direct piezo coupling to the skull with a very thin layer of coupling agent. So what I did was, to ensure I was keeping the heat pass low enough, I actually took a skull and explanted it. So I just cleared it out, and I took a thermal camera, and on the left-hand side here, you're looking at an image, a thermal image of the inside of the skull while I am passing a high voltage across my piezo, something like 100 volts alternating current. And here you can see that it's at 28.3 degrees Celsius at this time. And I basically just tried different pulse width. So here on the right-hand side, you can see I tried 300, 200, and 100 millisecond pulses at 1 hertz. So basically like 30% duty cycle, 20%, and so on. And I just looked at what happened to the temperature of the skull over time. And you can see that after 10 minutes of passing this alternating current, if it was at 30% duty cycle, or 300 milliseconds, that temperature actually rose above around 37 or 38 degrees Celsius. So that's above the physiological normal range of the brain temperature. And if you do that, yeah, we're only going a degree or two above that range, but that could be like inducing a fever, and that could be problematic. And again, this is at 30% duty cycle. So if I was at 100%, this effect would be very quick. So what I did here was to look at different duty cycles down to 10%, where I'm virtually not changing the brain temperature in any normal way. So at 100 milliseconds here, the change is so far below what the normal brain temperature is anyway, that it's unlikely to have an effect on neural activity. So just something to consider. This probably wouldn't have an effect if your transducer was at a distance. from your prep and you had a large volume of coupling agent. But again, something to think about. And Kim, you can comment on this.
Yeah, so Keith, let me just see if I understand this correctly. So your transducer was pointing the ultrasound through the skull?
Mm-hmm.
Okay, so, but then it was unclear whether the temperature rise was due to the absorption of the ultrasound in the skull or the fact that the transducer was heating up.
Right, so it could be a combination of both. If you look at the ultrasound transducer itself, it gets much hotter than this. And the reason I didn't just show you the one with the ultrasound itself is because, the skull actually has some sort of dissipating and resistance to the heating. But Kim is right, the skull is going to absorb some of the focused ultrasound, and that will combine with our effect.
Hmm. Yeah, okay. So transducer heating is definitely something to be aware of. Plus it can damage the transducer.
Mm-hmm.
Okay, so last one here that we listed is this ultrasound artifact. So we did some experiments. In fact, this came out of the experiments with the sheep studies that we were doing, where we had the electrodes on their head and they were measuring the visually evoked potential. So that worked fine when we had light only. We were looking at the light only stimulus. We had ultrasound that was at a different time than the light stimulus and the visually evoked potential we were measuring, and that all worked great. But in the portion of the stimulus, and so we interleaved, light only with ultrasound only. And this is what the data that we got from the ultrasound only, not in the sheep, but in a tofu phantom. And so it sort of looks like this, where we have the transducer up here. We've got our tofu. This is the water membrane that's coupling the transducer into the tofu. And then this is the electrode in the tofu. And what we were seeing is that when we put the ultrasound on, it's 300 milliseconds on, that there was a measurement in the electrode that looked like this. And so, this was like sort of about on the size of what we were measuring with the visual evoked potential. So definitely kind of a bit of a messy problem to intersperse this into the signal or have this overlapping on top of the signal. I'm not sure that we've totally solved this problem. Our theory as to why this was happening is that when you use a piezoelectric, what you do is you put a voltage across the crystal itself, so that one side is a different charge than the other side, and that in itself can generate electric fields, and the electric fields could then interact with the electrode. So that's sort of our thought as to why this was happening. It's definitely, it goes on during the ultrasound's on, and it goes off during the ultrasound when the ultrasound is off. So we tried a number of different methods to try to eliminate this. We decoupled it, it still happened, and never really got rid of it. And so one of the questions that we still haven't quite resolved is whether or not we can just sort of take the data and if this is a very reproducible artifact, to sort of extract that from the data itself and see what was remaining in the data. But just something to keep in mind. This was...
Yeah, I would say, sorry, Kim, just to comment, one way to sort of get rid of artifacts, and Kim's alluding to it, is if you can either remove the ultrasound itself while still producing the artifact, or if you can eliminate any possibility of the tissue effect, then you can subtract out. For instance, if I took a dead tissue and I still performed the ultrasound delivery and I saw what that signal looked like, I know that the tissue can't respond because it's dead, but I know that the artifact looks a certain way. And then Kim is mentioning you can, subtract that value away and then look what's left.
Right. So like in this case, this is clearly not physiologic since it was in the tofu. And so you could say, well, if this is always going to be in the data, then I just have to extract something of this form from the data. And it might be scaled differently, but it's always going to be of that form. Okay, well, so Keith, I think that's all we have lined up for today in terms of artifacts and confounds. I don't think we mean that this is all there is. This is really just all we were able to sort of think about for today.
Yeah, and the jury's not out. So, everyone in the field that, may get to see these lectures may have different opinions on them. And we're open to that. We just wanted to make everyone aware of sort of some general notions on it.
Yeah, and I think it'll be really helpful to have sort of discuss these because, and this point in the class, because it kind of follows on from some of the other discussions, but also as we lead into some of the experimental presentations that we get, that you'll have these in mind, that these are things to think about and be aware of. Okay, well, is that it, Keith?
Yeah, that's it.
Okay, probably a short lecture today. So, all right, see you later.